Grounding the incoming and outgoing cable shields to the ground bar in the pedestal is a proper practice to protect against lightning and power surges. The grounding scheme where the cable shield connects to both the pedestal ground and the seg MGB and ground field creates a potential ground loop due to multiple grounding points for the entrance cable shield. The noise is likely induced into the cable from the nearby transformer and power line. To break the ground loop, disconnect the entrance cable shield from the seg and leave it isolated. Alternatively, consider using an optical isolator to isolate the ground paths. Consider installing a signal ground. Create a dedicated signal ground bus and connect the shield of the entrance cable and the MDFGB to it. Isolate the signal ground from the NGB and ground field. Typically, transformers and power towers are grounded independently. If necessary for safety or coordination with other grounding systems, a minimum separation distance of 100 feet is recommended. To further isolate the power source, temporarily disconnect the transformer to verify if the noise disappears. Verify the grounding system integrity by checking the condition of the ground rods, connections, and ground field. Use a noise bridge to measure the noise level at different grounding points to identify the source. For complex grounding issues, it is advisable to seek professional guidance. When it comes to best practices for grounding, use a single-point grounding system for both electrical and telecommunications equipment. Isolate sensitive equipment and circuits from noisy sources. Use dedicated ground buses for different systems, for example signal, power, and lightning protection. Avoid creating loops or multiple grounding paths. Understanding ground loops is crucial in telecommunications to mitigate noise and ensure system reliability. Ground loops occur when there are multiple paths to ground, creating a circuit that can induce unwanted currents and noise into sensitive equipment. These loops can arise from various grounding configurations, especially in systems where grounding points are not properly coordinated. Identifying and breaking these ground loops is essential for maintaining signal integrity and preventing equipment malfunction. One common scenario where ground loops occur is in telecommunications sites where equipment is grounded at multiple points. For instance, an equipment rack might be grounded to both the building's grounding system and a separate grounding electrode. This dual grounding creates a loop that can pick up electromagnetic interference, EMI, and other electrical noise, leading to disruptions in signal transmission. A systematic approach to diagnosing and resolving ground loop issues begins with a thorough inspection of the grounding system. It's important to verify that all grounding connections are secure, corrosion-free, and properly sized according to applicable electrical codes. A visual inspection can often reveal obvious problems such as loose connections, corroded conductors, or improper grounding techniques. Following the visual inspection, electrical testing should be performed to measure ground impedance and voltage differentials between grounding points. High ground impedance can indicate a poor grounding connection, while voltage differentials suggest that current is flowing through unintended grounding paths. These measurements can help pinpoint the location of ground loops and identify areas where grounding improvements are needed. Several techniques can be employed to break ground loops and mitigate noise. One common approach is to use a single-point grounding system where all equipment is grounded to a single, central grounding point. This eliminates the possibility of creating multiple grounding paths and reduces the risk of ground loop formation. Another technique is to use isolation transformers or optical isolators to break the electrical connection between equipment while still allowing signal transmission. These devices prevent current from flowing through the grounding system, effectively isolating the equipment from ground loop noise. In addition to these techniques, proper cable shielding and grounding practices can also help reduce ground loop noise. Shielded cables provide a barrier against EMI and can be effective in preventing noise from entering the signal path. Grounding the cable shield at only one end can further minimize ground loop formation by preventing current from flowing through the shield. Effective grounding is a critical aspect of electrical safety and equipment protection in any facility. Proper grounding ensures that electrical faults are safely conducted to ground, minimizing the risk of electric shock and preventing damage to equipment. However, a poorly designed or improperly installed grounding system can create more problems than it solves, including ground loops, increased noise levels, and even equipment damage. Understanding the principles of grounding and implementing best practices is essential for maintaining a safe and reliable electrical system. The primary purpose of grounding is to provide a low impedance path for fault current to return to the source. This allows protective devices such as circuit breakers and fuses to quickly detect and interrupt the fault, preventing further damage or injury. A properly grounded system also helps to stabilize voltage levels and reduce electrical noise, improving the overall performance and reliability of electrical equipment. There are several types of grounding systems commonly used in electrical installations, each with its own advantages and disadvantages. One common type is the equipment grounding system, which connects all non-current carrying metal parts of electrical equipment to ground. This includes things like metal enclosures, conduits, and equipment frames. The equipment grounding system provides a path for fault current to flow back to the source, allowing protective devices to trip and clear the fault. Another type of grounding system is the neutral grounding system, which connects the neutral point of the power supply to ground. This system is used to stabilize voltage levels and provide a reference point for the electrical system. The neutral grounding system also helps to reduce the risk of electric shock by providing a low impedance path for fault current to return to the source. In addition to these basic grounding systems, there are several other grounding techniques that can be used to improve electrical safety and performance. One such technique is to use ground rods to provide a direct connection to earth. Ground rods are typically installed near the electrical service entrance and connected to the grounding electrode conductor, which in turn is connected to the equipment grounding system and the neutral grounding system. Ground rods help to dissipate fault current into the earth, reducing the risk of electric shock and preventing damage to equipment. Another important grounding technique is to use bonding jumpers to connect metal parts together. Bonding jumpers are short lengths of wire or metal straps that are used to connect metal conduits, enclosures, and other metal parts to the grounding system. Bonding jumpers help to ensure that all metal parts are at the same electrical potential, reducing the risk of electric shock and preventing the buildup of static electricity. When designing and installing a grounding system, it's important to follow all applicable electrical codes and standards. These codes provide detailed requirements for grounding system design, installation, and testing. Following these requirements helps to ensure that the grounding system is safe, reliable, and effective in protecting people and equipment. One of the most important considerations when designing a grounding system is to minimize ground impedance. Ground impedance is the resistance to the flow of fault current through the grounding system. High ground impedance can prevent protective devices from tripping quickly, increasing the risk of electric shock and equipment damage. To minimize ground impedance, it's important to use properly sized grounding conductors, make secure grounding connections, and minimize the length of grounding conductors. Regular testing and maintenance are essential for ensuring the continued effectiveness of the grounding system. Grounding system testing should be performed at least annually to verify that all grounding connections are secure, that ground impedance is within acceptable limits, and that protective devices are functioning properly. Any problems identified during testing should be promptly corrected to prevent potential electrical hazards. In addition to testing, regular maintenance should be performed to keep the grounding system in good condition. This includes inspecting grounding connections for corrosion, tightening loose connections, and replacing any damaged or deteriorated components. Proper grounding is not just a matter of following the rules and regulations. It's about understanding the principles of electricity and applying them to create a safe and reliable electrical system. By taking the time to design, install, and maintain a high-quality grounding system, you can protect people and equipment from the hazards of electricity and ensure the continued performance of your electrical system. Noise in telecommunications systems can significantly degrade performance and reliability. Understanding the sources of noise and implementing effective mitigation techniques are crucial for maintaining signal integrity and ensuring reliable communication. Noise can originate from various sources, both internal and external to the system. Internal noise is generated by the components within the telecommunications equipment itself, such as thermal noise, shot noise, and flicker noise. External noise comes from sources outside the equipment, such as electromagnetic interference (EMI), radio frequency interference (RFI), and power line noise. Thermal noise is caused by the random motion of electrons in conductors and semiconductors. It is present in all electronic components and increases with temperature. Shot noise is generated by the random arrival of charge carriers at a junction, such as in a transistor or diode. Flicker noise, also known as 1/F noise, is a low-frequency noise that is often associated with imperfections in semiconductor materials. Electromagnetic interference (EMI) is caused by electromagnetic fields generated by other electronic devices, power lines, and radio transmitters. EMI can be coupled into telecommunications equipment through radiation or conduction. Radio frequency interference (RFI) is a type of EMI that occurs at radio frequencies. RFI can be generated by radio transmitters, microwave ovens, and other sources of radio frequency energy. Power line noise is caused by fluctuations in the voltage and current of power lines. Power line noise can be coupled into telecommunications equipment through the power supply or through ground loops. There are several techniques that can be used to mitigate noise in telecommunications systems. One common technique is to use shielding to prevent EMI and RFI from entering the equipment. Shielding involves enclosing the equipment in a conductive enclosure that blocks electromagnetic radiation. Another technique is to use filtering to remove unwanted noise from the signal. Filtering involves passing the signal through a circuit that attenuates noise frequencies while allowing the desired signal frequencies to pass through. Grounding is also an important technique for mitigating noise. Proper grounding helps to reduce ground loops and prevent noise from being coupled into the equipment through the grounding system. Signal processing techniques can also be used to reduce noise. Signal processing techniques involve using algorithms to remove noise from the signal. One common signal processing technique is averaging, which involves averaging multiple samples of the signal to reduce the effects of random noise. Another signal processing technique is filtering, which involves using digital filters to remove unwanted noise frequencies. In addition to these techniques, proper cable management can also help to reduce noise. Proper cable management involves keeping cables short, routing cables away from noise sources, and using shielded cables. By implementing these noise mitigation techniques, it is possible to significantly improve the performance and reliability of telecommunications systems. The choice of which techniques to use will depend on the specific sources of noise and the requirements of the system. When dealing with grounding and noise issues, it's essential to understand the role of the master ground bar, MGB, and its relationship to other grounding elements. The MGB serves as a central point for connecting various grounding conductors within a facility, ensuring a common ground potential and minimizing voltage differences that can lead to noise problems. Typically, the MGB is connected to the building's main grounding electrode system, which consists of ground rods, grounding plates, or other grounding electrodes buried in the earth. This connection provides a low impedance path for fault currents to flow back to the source, allowing protected devices to quickly clear faults and prevent electrical hazards. In addition to connecting to the main grounding electrode system, the MGB also serves as a connection point for equipment grounding conductors, bonding conductors, and other grounding elements within the facility. Equipment grounding conductors are used to ground non-current carrying metal parts of electrical equipment, such as enclosures, conduits, and equipment frames. Bonding conductors are used to connect metal parts together to ensure that they are at the same electrical potential. By connecting all of these grounding elements to the MGB, a common ground potential is established throughout the facility, minimizing voltage differences and reducing the risk of electrical shock and equipment damage. The MGB also plays a crucial role in mitigating noise problems. Noise can be coupled into electrical and electronic equipment through ground loops, which are created when there are multiple grounding paths with different ground potentials. These ground loops can cause current to flow through the grounding system, generating noise that can interfere with sensitive electronic equipment. By connecting all grounding conductors to a central NGB, the impedance of the grounding system is minimized, reducing the voltage differences between grounding points and minimizing the formation of ground loops. In addition to minimizing ground loops, the NGB also provides a convenient point for connecting surge protection devices. Surge protection devices are used to protect electrical and electronic equipment from voltage surges caused by lightning strikes, power line transients, and other events. By connecting surge protection devices to the NGB, surge currents are safely diverted to ground, protecting sensitive equipment from damage. When designing and installing an NGB, it's important to follow all applicable electrical codes and standards. These codes provide detailed requirements for NGB size, construction, and installation. It's also important to ensure that the NGB is properly labeled and accessible for inspection and maintenance. Regular inspection and maintenance are essential for ensuring the continued effectiveness of the NGB. The NGB should be inspected at least annually to check for loose connections, corrosion, and other signs of damage. Any problems identified during inspection should be promptly corrected to prevent potential electrical hazards. Power transformers can sometimes be a source of noise in telecommunications systems. The electromagnetic fields generated by transformers can induce noise into nearby cables and equipment, particularly if the transformer is not properly grounded or shielded. Additionally, transformers can generate harmonic distortion, which can also contribute to noise problems. To mitigate noise from power transformers, it's important to ensure that the transformer is properly grounded and shielded. Grounding the transformer enclosure and core helps to minimize the electromagnetic fields that can be radiated into nearby cables and equipment. Shielding the transformer with a metal enclosure can further reduce the electromagnetic fields. It's also important to ensure that the transformer is properly sized for the load. An undersized transformer can be overloaded, which can lead to increased harmonic distortion and noise. Using a properly sized transformer can help to minimize these problems. In addition to these measures, it's also important to keep telecommunications cables and equipment away from power transformers. Routing cables away from transformers can help to reduce the amount of noise that is coupled into the cables. Using shielded cables can also help to reduce noise. If it's not possible to keep telecommunications cables and equipment away from power transformers, then it may be necessary to use filters to remove noise from the signal. Filters can be used to attenuate noise frequencies while allowing the desired signal frequencies to pass through. There are several types of filters that can be used for this purpose, including low-pass filters, high-pass filters, and band-pass filters. The choice of which filter to use will depend on the specific frequencies of the noise and the desired signal. In addition to these techniques, it's also important to consider the overall grounding system when dealing with noise from power transformers. A poorly designed or improperly installed grounding system can create ground loops which can increase noise levels. Ensuring that the grounding system is properly designed and installed can help to minimize ground loops and reduce noise. It is important to consider the location and grounding of high-voltage power towers in relation to telecom infrastructure. High-voltage power towers can generate significant electromagnetic fields that can induce noise into nearby telecommunications cables and equipment. The closer the power tower is to the telecom infrastructure, the greater the potential for noise interference. To minimize noise interference from high-voltage power towers, it's important to maintain a safe distance between the power towers and the telecom infrastructure. The recommended minimum distance will vary depending on the voltage of the power line, the type of telecom equipment, and the sensitivity of the telecom equipment to noise. As mentioned earlier, a separation distance of 100 feet is recommended. In addition to maintaining a safe distance, it's also important to ensure that the power towers are properly grounded. Grounding the power towers helps to minimize the electromagnetic fields that can be radiated into nearby cables and equipment. The grounding system for the power towers should be designed and installed in accordance with applicable electrical codes and standards. It's also important to consider the grounding of the telecom infrastructure in relation to the power tower grounding system. If the telecom infrastructure and the power towers share a common grounding system, then there's a greater potential for noise to be coupled into the telecom infrastructure. In this case, it may be necessary to isolate the telecom infrastructure grounding system from the power tower grounding system. This can be achieved by using isolation transformers or optical isolators. When planning the location of new telecom infrastructure, it's important to consider the proximity of high-voltage power towers and to take steps to minimize potential noise interference. The best approach is to locate the telecom infrastructure as far away from the power towers as possible. If this is not possible, then it may be necessary to use shielding, filtering, and other noise mitigation techniques to protect the telecom equipment from noise interference. Furthermore, regular monitoring of the noise levels in the telecom infrastructure can help to detect and address any noise problems before they become severe. Noise monitoring can be performed using spectrum analyzers and other noise measurement equipment. If excessive noise levels are detected, then it may be necessary to take corrective actions, such as improving the grounding system, adding shielding, or relocating the telecom equipment. Effectively mitigating noise in telecommunications systems requires a combination of careful planning, proper grounding and shielding techniques, and ongoing monitoring and maintenance. By taking these steps, it is possible to ensure that telecommunications systems operate reliably and without interference from external noise sources.